Okay.
Okay, so we need, I know this is really a pain, but you really do need to draw a new picture. So I'm going to just do it because that's what we need to do. And I'm going to draw it slightly differently than what it looks like here. I mean, this is, what do we call this? This is a linear graph, where you just kind of get rid of those corners that really are not meaningful at all, because really this is just a wire going here. And it kind of shows you more the logic of what's going on. So this is V2 over. Okay, so there's the picture redrawn. Do I have everything? I've got the 20, that's an ohm symbol there. 20 kilo ohm resistor, the current I1 in that branch, 2 volts. I've got the voltage controlled dependent voltage source. I've got the current controlled current source. Okay, so I think I've got it. Where is ISC? Well, ISC is the short circuit between the terminals that you're looking at. I don't want to draw it here because then that would destroy the picture that I used to get VOC, but it basically just shorts out the terminals A and B. So here it is, and then you just show the current in that wire. So there's ISC. So this is now the new problem. As soon as I solve this problem for the short circuit current, then I'm done with the entire problem. Because then I finally found the Thevenin resistance, because RT is equal to, well, I erased it, but RT was equal to VOC over ISC. We just found VOC, now we've got ISC. Once you have that, then you've got the maximum power. Okay, so it's a new problem. Let's use mesh current analysis, because we use node voltage on the other one, so we might as well use mesh current on this one. Before I do that, though, I notice that I have a resistor in parallel with a short circuit. What happens in that case? What's the equivalent resistance? It's 0. So I can erase this. Kyle didn't like that. Okay, let me put it back. Okay, so this was what, I don't even care what it was. It could be 2 million K, whatever. It's in parallel with this short circuit. So if you look at, if we redrew this, okay, terminals A and B, we have, here's the short circuit, and then here's that resistor that could be 2 million ohms. What's the equivalent resistor between A and B? For two parallel resistors, it's the resistance of this times the resistance of this over this plus this. So it's 0 over 2 million, but it's 0, so it's 0. So it's just a wire. So that's why I can just get rid of it. And now if you kept it in there, you'd still get the right answer, but it would be more painful. The math would be harder. So okay, we're going to go through those steps. By the way, you don't have to put this on your paper, do like the Super Kaufman. In fact, don't. just follow the steps, but don't actually put it on your paper, because then, like if you go and take the engineering and training exam and you have that, they won't know what you're talking about. So draw. Okay, we did that step. Label. Okay, so label means we're using mesh current analysis. We've got to label the mesh currents. We've only got 2 meshes here. So I'll show these 2 mesh currents. I can just label this one ISC, right? Because that's exactly what it is. I could have also labeled it 100 I1. Either would work, but since I'm looking for ISC, it's kind of nice to label it ISC. This one, I'll label I1 because it's the same current as I1 that you show here. By the way, be very careful. Never label something with, that already has, what am I trying to say? Like if I had a current here labeled I2 and then I called this I2, I mean that would be bad, right? Because they're not the same current. So just be careful not to do that kind of thing. Okay, so I've labeled my mesh currents, so I'm done with that step. Do I have dependent sources? Yes, I do. So I need to write the controlling quantity of my dependent sources in terms of the mesh currents in this case, right? Because the mesh currents are the variables. Okay, I kind of lost V2, so I have to go back here. What was V2? It was the voltage between A and B. So it still exists, sort of. V2 is the voltage between A with respect to B. What is it? It's a short circuit, 0. So this dependent source, the controlling quantity, is 0. Well, that's interesting. So that actually means this is a short. Okay, but that's okay. This controlling quantity, I1, can I write that in terms of mesh currents? Well, yeah, it actually already is. Okay, that was trivial. And it's because I intentionally labeled this mesh current as I1. If I had labeled it IA, then in this step you would have seen that IA is equal to I1. So I saved myself a little bit of time, I guess, maybe. But okay, so that's that step. And then the super step. So this step has to do with current dependent, or really dependent or independent, just any current source. You look for current sources and you identify super meshes. Well, we do have a current source, but there's no mesh on the other side. So there's really no super mesh to deal with. So really, there's nothing to do with that. There's nothing there. And then the last step in this case, because we're doing mesh current analysis, we'll be doing Kirchhoff's voltage law. For any, okay, and this is important to remember, for any mesh that doesn't have a current source on the perimeter. Okay, so we actually don't have to do it for this one because this has a current source on the perimeter. So we only have to do it for this one. So Kirchhoff's voltage law for, and I'll just say for left mesh. I don't care how you identify it, just make sure I know what you're talking about. I guess you could call it mesh 1 because we labeled the mesh current there I1, so that would have been clear too. But just make sure I know where you're taking Kirchhoff's voltage law. So Kirchhoff's voltage law for the left mesh is going to be, I guess I'll start here. Minus 2 millivolts plus 2K times I1. Well, this looks kind of weird where I put that subscript there. That looks better. 2K times I1 plus V2 over 5,000. I mean, I suppose we could put that there, but we already know that V2 is 0. I don't know, you could put it there and then show it as 0, or I guess just say 0. And then we're done. Is equal to 0. So I've got I1. I1 is equal to, just solving this equation. Oh my God, I can't do math. 2 milli over 2K, is that right? So that's 2 micro.
1 micro.
1, yeah, 2 divided by 2 is 1, thank you. Okay, so I1 is 1 microamp. Okay, so what's ISC? Well, going here, the reason why we don't have to do the Kirchhoff's voltage law for a current source on the perimeter, first of all, we wouldn't know the voltage across the current source. But we can see the relationship between the mesh current and the current source on the perimeter. We see that 100 I1, the current in here is just, it's going in the opposite direction as ISC. So it's just ISC is equal to minus, maybe I do it this way. ISC is equal to minus 100 I1. And we just found out that I1 is 1 microamp. So now we've got ISC is equal to minus 100 times 1 micro. Well, anyway, we're done. We found ISC. And we're happy. Cut it.